Hi and welcome to Section 2, Deployment of Collection and Message Queuing Tiers. In this video, we will focus on the collection tier, more precisely on the general aspects of collecting or ingesting a data stream. As you can see here, we have a nice agenda focused on the interaction between the collection tier and the streaming data API that serves a data stream. Mainly, we will talk about different interaction patterns and different protocols for ingesting data. But we will also take a look to a specific scaling issue. So the collection tier overview is our first target. On the streaming blueprint architecture diagram, we can easily notice that the collection tier stands between the streaming data API, Meetup RSVP API in this case, and the message queuing tier. If we try to put our diagram in words, we can say that the collection tier is needed for bringing data into our pipeline. So the collection tier is actually an application capable to communicate with the source of data via a streaming data API. In our case, we will write a Spring Boot application that uses the Spring WebSocket API to communicate with the Meetup RSVP WebSocket endpoint. After ingesting the data via the push or pull mechanism, the collection tier application must be capable to send the data to the message queuing tier. In our case, we have to rely on the push mechanism, since the Meetup RSVP endpoint is a push only. Between ingesting and sending the data, the collection tier application can optionally perform other tasks. In our case, we will not perform any extra task, but pay attention that whatever you may choose to do here will add a delay in processing data, and if these tasks are time consuming, you can slow down the ingestion process. Okay, so far so good. Now let's discuss about some typical interaction patterns. We are talking about the interaction patterns that can be used between the collection tier and the streaming data API. So let's start with the request response pattern. The request response pattern is very common since it is the pattern used to browse the internet. We open the browser and we fire a request, for example, a Google search, and we wait for a response. While waiting, we cannot perform other tasks, which means that this is a synchronous pattern. From streaming perspective, this approach can be okay only if the potential delay is acceptable. So, the cost of the collection tier having to wait for a response and the streaming data API having to respond in a timely fashion are the main drawbacks of this interaction pattern. But the advantage is that this interaction pattern is very easy to implement. Now, a flavor of the previous interaction pattern imposed the collection tier to be asynchronous. This is known as the half-async pattern. When we interact with a backend API that has a high latency, using synchronous requests may result in many outstanding requests, which requires a large number of threads to make enough parallel connections. On the other hand, using a synchronized handling allows the response to be decoupled from the request. In other words, the collection tier can perform other tasks while waiting for the streaming API to respond with a brand new set of data. The main result is an overall increase in the work performed by the client. So this is useful if you know that your collection tier should perform some extra tasks that are independent of the current request. Now, if you decide that this is a good choice for you, then it is recommended to rely on a framework that comes with asynchronous support, such as Netty, Play, or Node.js. Mainly this will simplify and speed up the implementation time. But in the modern applications, we prefer to have a full asynchronous approach. This is another flavor of the request response pattern, where both the collection tier and the streaming API perform their work asynchronously. This can be a good choice, and you should consider it every time is your responsibility to implement the streaming API as well. Again, it is recommended to rely on frameworks that comes with asynchronous capabilities. For example, we can rely on a full async implementation for a real-time communication between an airport control tower and the aircraft. We can develop a streaming system that will live inside of each aircraft. This system is capable to collect data from the airport control tower in an asynchronous fashion. This means that while waiting for the control tower to respond, each aircraft can collect data from other aircrafts as well, or perform other tasks, like pushing the current data through its streaming pipeline. In addition, the Airport Control Tower Streaming Data API is asynchronous as well, so it will be capable to handle a lot of requests from aircrafts. Okay, now let's talk about the request acknowledge pattern. In this case, the side that triggers the request is not expecting for a response, is expecting for an acknowledgement that the request was received successfully. The data sent back in the acknowledgement can be added in the next request, maybe to check the status of the initial request or get a final response. For example, as you can see in the picture from the left side, the collection tier can rely on a push data mechanism, which means that the streaming API will make the request and will push some data to the collection tier. The collection tier responds with an acknowledgement, and in the next request, the streaming API will add this acknowledgement as well. This way, the collection tier can uniquely identify the request source. Now, on the other hand, as you can see in the picture from the right side, the collection tier is triggering the request and the streaming API responds with an acknowledgement. Basically, in this case, the collection tier is collecting acknowledgements, which, for example, can be used for heartbeats stats. Here, we have a streaming system based on the request acknowledge pattern. Our system provides information to its clients about a printing center lifespan. Now, in this context, let's see two possible scenarios meant to highlight the acknowledgement-based interaction pattern. In the first scenario, each printer sends a request to the collection tier containing its status, like ready to print, not available for printing, no more paper, no more ink, and so on. At first request, which doesn't contain an acknowledgement, the collection tier responds with an acknowledgement that uniquely identifies that printer. At next requests, the printer will add the acknowledgement as well, so the collection tier knows exactly from which printer it just received the status. Now, by grouping the status data by printer, we can easily isolate the status trend of each printer over time and provide different stats, like which is the most used printer in the printing center. In other scenario, let's suppose that our streaming system relies on heartbeats to provide stats about the printer's health. So every second, the collection tier will send to each printer a request of type "Are you there?" Every time, the printer will respond via an acknowledgement, or it will not respond at all. So the collection tier can use this acknowledgement to track the online-offline rate of each printer during its lifespan. Okay, now let's discuss about the publish-subscribe pattern. This is a very used pattern in message-based data systems such as Apache Kafka. Typically, a handful of producers send their data to a broker, and consumers exploit this data. Producers can be consumers as well, and vice versa. Now, from streaming perspective, the collection tier can act as a consumer, but it can be a producer as well. The streaming API is represented by a broker that acts as a message backbone. The broker comes with topics which uses different topologies to isolate access to data for producers and consumers, and provides logical grouping for messages. For example, An airport control tower can act as a broker for the aircrafts. Each aircraft has an onboard streaming system that contains a collection tier capable to subscribe to certain topics of the broker and ingest data from them. But in the same time, each aircraft can produce data. For example, the collection tier can augment the ingested data and send it to another topic, or the results from the stream analyzer can be sent to a topic. This way, the aircrafts can set up communication channels between them and they can exchange data in a streaming fashion. Okay, now let's talk about the one-way pattern, also known as the fire and forget message pattern. This is useful when a system can trigger a request without expecting a response. For example, a streaming API of a sensor can send every 50 milliseconds a request containing its data to a collection tier, without receiving any kind of response from this tier. And this is normal, since for the sensor, a response will be pointless. Well, while this interaction pattern is a great fit for emitting data extremely fast, it has the drawback that some data may be lost forever. But thanks to the big volume of data per tiny unit of time, in most of the cases, this loss is acceptable. For example, let's suppose that we have a streaming system that is capable to ingest the positions of our robots and output their paths. The positions are collected at every 50 milliseconds. But what are the arguments for choosing the one-way pattern in this case? Well, first, we need to ingest data very fast. Secondly, sending a response to the robots is pointless. And third, if some positions are lost, will not affect the final paths. Even if we lose the positions for several seconds, we can still approximate the paths based on a simple interpolation algorithm. Well, the final pattern is the stream pattern. In this case, the collection tier triggers a single request to the data streaming API. This will result in a persistent connection between them. And further, the collection tier will consume the data as a stream. Or in other words, the response is a continuously flow of data. Well, this is the pattern that we will use. We will connect to the Meetup RSVP WebSocket API and we will start ingesting data via a persistent connection. Even if we have a bidirectional connection, the Meetup RSVP is a push-only endpoint, which means that it will ignore any message that we send. Okay, we covered a set of interaction patterns, and now it's time to check out some protocols used by the streaming API for sending data and by the collection tier for ingesting data. The first protocol is webhooks. This protocol relies on registering callbacks or endpoints that will be notified for changes. For example, GitHub uses this protocol to expose different kind of endpoints to its clients. Mainly, this protocol has two steps that can be described in a streaming system like this. In the first step, the collection tier sends a request to register the callback via HTTP post. Sometimes this step is done manually by a user that will fill up the needed information on a website. In the second step, when new data arrives or some specific event takes place, the streaming API calls via HTTP post all the registered callbacks. When you consider this protocol, keep in mind that the latency of data going over HTTP is average. In addition, this protocol is unidirectional, always from the streaming API to the collection tier, which means that supporting fault tolerance will be an issue. For example, we cannot acknowledge the streaming API that we received the data. And since it relies on HTTP post requests, is not a good fit for a high rate of updates as well. In conclusion, this protocol has a low efficiency. Okay, now let's discuss about HTTP long polling. In this case, the collection tier opens a connection via an HTTP GET request. The streaming API holds this connection open until there is a new data to be sent. In turn, the collection tier immediately opens a new connection and the cycle is repeated. Since this protocol relies on HTTP, it has an average latency and is not a good fit for a high rate of updates. For example, think to the overhead of closing the connections and the collection tier having to reopen them. Nevertheless, it should support a higher rate than webhooks, something like the rate of a chat application. Now, even if we can consider this protocol as bidirectional, achieving fault tolerance is our job, exactly as in the case of webhooks. In conclusion, if we consider the rise of asynchronous programming in client-side, we can consider HTTP long pooling as a protocol with an average efficiency. Now, the server-sent events protocol is a unidirectional protocol based on HTTP, and it represents an improvement of the HTTP long polling protocol. In this case, the collection tier will connect to the streaming API, and the connection remains open until the collection tier will close it. Meanwhile, the streaming API can push updates through this single connection, which results in an efficient way of exploiting the network. Now, this protocol has an average latency and no fault tolerance support, but we can address some fault tolerant aspects, such as ensuring that the streaming API doesn't miss sending data to the collection tier. Since the network is used in a more efficient way, this protocol supports a higher rate of updates than HTTP long polling. In conclusion, the server-sent events protocol has a good performance and allows us to provide a more resilient API, placing it in the category of a high-efficient protocols. Now, the server-sent events push proxy is a variation of the traditional server-sent events. This variation is useful for mobile devices in order to save some battery. The last protocol that we discuss is WebSocket. This protocol is a full duplex protocol that uses TCP for the communication transport. WebSocket uses HTTP for the initial handshake and protocol upgrade request, and then switches to TCP. This means that the streaming API sends updates to the collection tier via TCP. The connection can be closed at any moment by the collection tier or the streaming API. Thanks to the fact that TCP is used for communication transport, this protocol has a low latency and supports a high rate of updates. It is bidirectional from beginning to end. It allows us to build fault-tolerant and reliable semantics into it. This is one of the most used protocols for streaming, and it has a high efficiency. Well, we end up the discussion about protocols here, but you may want to check data distribution service and MQ telemetry transport as well. Okay, now let's condense this information in a comparison of protocols table. So consider this table as a handy guideline in order to decide which protocol is the proper choice for your streaming systems. Okay, it's time to go further and discuss about scaling the collection tier when we rely on a protocol that keeps a direct and persistent connection open, such as the WebSocket protocol. So let's check this diagram containing the streaming API, a collection tier of horizontal scaled collection nodes, and the message queuing tier. Notice that 2 of the 3 nodes of the collection tier are useless, because there is a direct and persistent connection between the streaming API and the first node that handles the stream ingestion. So WebSockets are powerful for real-time applications, but it's also what makes it more difficult to scale. A possible solution to this problem consists in relying on a buffer layer in the middle. In this case, a single collection node that was vertically scaled to its limits will ingest the stream and, as quickly as possible, it will push the data to the buffering layer without applying any business logic. Next, a set of collection nodes that can be further horizontally scaled will read from this buffer layer and may perform the business logic. Another approach relies on using a full-featured broker, such as Kafka or RabbitMQ. Each application instance connects to the broker, and messages broadcasted from one application instance can be broadcasted through the broker to WebSockets clients connected through any other application instances. Well, that's all for now. As this summary reveals, we have covered a lot of topics in this video. Now it's time for a well-deserved break.